In this lecture, we're going to look at the example of the two tanks that flow into each other, and we would like to know what happens to the concentration as the liquid flows from one tank to the next tank. So the inflowing concentration is called Ci, and then the outflowing concentration of tank 1 is C1, and the outflowing concentration of tank 2 is C2. And we've identified the model for this. The modeling equation was V times dC over dt equals to Q times Ci minus C. And we have two equations for this. And if we stick in the relevant numbers, a volume, for example, of 4 cubic meters and a flow rate of 2 cubic meters per hour and volume of 3 cubes for the second container, we get the following differential equations. So the first one is 4 times the concentration in tank 1 over dt plus 2 times C1 equals to 2 times Ci. And the second one is, because this tank's a bit smaller, 3 times dC2 over dt plus 2C2 equals to 2C1. So now we want to know what happens if we change the concentration. So the idea is to have a concentration, Ci, that changes for 0.25 minutes to 6. So the initial value is 1, and then it goes up from 1 for a short period of time to 6. So I know it's a little bit difficult to understand, but to mathematically make it easier, I'm going to assume that it goes from 0 to 5. And later on, we will just change it from 1 to 6 by adding the base concentration of 1 to the overall result. And this is fine because this dynamic equation is linear. That means it's true for all operating conditions. All these basic forms here of the model are normal, ordinary differential equations, and that means we can, they are linear in the sense that it doesn't matter at what point I start. So it's fine to not use change the concentration from 1 to 6, but instead change it from 0 to 5 and then move it up at the very end by 1. This way, we're making our life a lot easier mathematically. Then I also want to point out, this one is a pulse. So Ci of t is Ci P of t. Well, we can also approximate the pulse with a delta pulse because it's quite short and quite high. So what we say is we call the Ci of delta of t, and it's a delta pulse. The only question now is, what is the height of the delta pulse? The normal height of a delta pulse is 1, because it's assumed that the integral over this infinitely short time, but this infinite amplitude, is the integral of this arrow is 1. So now the integral shouldn't be 1, but it should be equal to the area under this curve. And the area under this curve is 5 times 0.25. So this means that we should have a delta pulse with a height of, or multiplied with 1.25, because this is 5 times 0.25 equals to 1.25. And so this delta pulse has a height that is of 1.25. And then we're assuming that the concentration at time t equals to 0 is the same everywhere. And in our case, we're not going to assume it's 1, but we're going to assume it's 0. So we're saying it starts at 0. So now we would like to know what is C1 if I have delta input over time. I want to know how does it compare to the pulse. And I want to know the same for C2. What is C2 for the delta pulse? And what is C2 for the actual pulse? Okay. And for this, I need a description for the inputs. So Ci delta of t, it's just what we said, is it equals to 1.25 times delta of t. Whereas the input of the pulse, this pulse can be described as a step upwards minus a step downwards. So it's a step upwards, so it's 5 times a step function. But then I have to step down, so I have to go minus step by 5. But now I need a shifted step and shifted by 0.25 to the right. And remember, if we're shifting to the right, we are saying t equals to 0.25, because if we're setting t equals to 0.25, we're getting t minus 0.25 minus 0.5 is 0. So we're shifting it to the right by subtracting the time delay. Okay, just as a reminder. All right. So now we would like to, let's start here with C1. So let's start with the upper part here. We're just only interested in C1 because once we have C1, maybe we can figure out what C2 is. And we've done that. I'm just repeating it. Okay, so let's have a look. We have our differential equation, which I've just moved away from the screen, which was this guy here. 4 times dc1 over dt plus 2c1 equals to 2 times ci. So I'm just going to copy it down here again. 4 times dc1 over dt plus 2c1 equals to 2ci. Okay. So what we need to do now is we need to do the Laplace transform of the equation. And for this, we need to use number 24 in our transformation list. So number 24 was Laplace of a differential dc1 over dt equals to s times c1 of s, so the Laplace transform of c1 time multiplied by s, minus c1 of 0. And this is why I've conveniently set this to 0. This is equal to 0. Okay, so if we plug this in, we're getting 4s c1 of s plus 2 times c1 equals to 2 times capital Ci, indicating it's the Laplace transform. And now, at this point, this is the differential equation. I haven't done anything. I can simplify it slightly, or I can simplify it by dividing it by 2, because I've noticed I've got a 4, I've got a 2, and I've got another 2. And so I just divide it. So I have 2s plus 1 times c1. I'm factorizing it out. The common term at c1 equals to ci, and then I solve it for c1. c1 equals to 1 over 2s plus 1 times ci. All right. So now I want to say, well, my input function is ci. I need to do the Laplace transform here of the input. My input was ci delta of t equals to 1.25 times delta of t. And I do the Laplace transform using rule number 1. And that is that the Laplace transform of a pulse is simply 1. So I have Ci delta, so capital C, of S equals to 1.25. And if I stick this in here, I can get an expression for C1 in the Laplace domain. So it's 1.25 divided by 2S plus 1. Now I can do the brave step and do the inverse Laplace transform. And I need to look into my table, and I'll find that I have, if I have the form 1 over tau s plus 1, that it corresponds in the time domain to 1 over tau e to the minus t divided by tau. And that is rule number 6. Okay, so I stick this guy in here, and then I get, and this now that I'm sticking this in, I get C1 delta of S. And if I do the inverse Laplace transform, I get C1 delta of T. And that is equal to, well, my tau here is 2. So it's 1/2 times 1.25 times e to the minus t half. And that is the half of 1.25 is 0.625 e to the minus t half. So this is my C1 delta of t, and this is the first bit that I was interested in, and I wanted to know what that looks like. So if I do a pulse, what do I get? Sorry, a delta pulse. Well, my C1 delta of t will look something like this. I start at 0.625, and I have a time constant of tau equals to 2. So tau equals to 2 is here. And I have a decreasing exponential function that goes something like this. So now the only thing we've done incorrectly is we have to shift the whole plot up by +1 because our concentration started at 1, and it will go back to 1. It won't drop below 1. So I should have underlined this here. So this is the normalized one, and my C delta C11, let's call it C11 because I've come from level 1, equals to 1 plus 0.625 e to the minus t half. Okay, so now I can draw a line under this. So this is the first question that I've answered. This is what the function will look like. So now I would like to compare it, if you're looking back up here to our list. So we've done this guy here. So now we would like to know what's happening with the pulse. So how does it compare to the pulse? And I can use the same equation that I had earlier on here, which is C1 equals to 1 over 2s plus 1 times Ci. But now I have to do the Laplace transform of the pulse. So just remember, Ci pulse of t was 5 times s of t minus s t minus 0.25. And if I do the Laplace transform of this, I get Ci of p of s, so capital letter, equals to 5 times. And now I have to take the Laplace transform of a step, and that is 1 over s. And this is using the Laplace transform number 2. So I do Laplace transform here again, and I use equation number 2. And I have step, so the step function, the Laplace transform of a step is 1 over s. And now I have to use the Laplace transform of a delayed step. So I have to use number 26. So 26 says, if I have a delayed function, I take the same function, but I have to multiply it with e to the minus the time delay, so of course not t, times s, like that. Okay. So now this is my input pulse, and it consists of two parts. The one part is the original part, this guy here, and then the other part is the delayed version. Okay, so let's carry on and stick this into this equation up here, which describes our general system. So now we have C1 P of S equal to 1 divided by 2s plus 1 times CIP, and that is 5 times 1 over s minus 1 over s e to the minus 0.25s. Okay. Now, these are two separate terms, so I should keep them separate, and this is why I marked the one blue and the other one red. So I'm going to do the same here now. So this is equals to 5 divided by s times 2s plus 1 minus 5 times s2s plus 1 e to the minus 0.25s. Okay. And at this point, I can take the inverse Laplace transform again. Now I want to know C1 of P of ft. So I take the inverse Laplace transform, and I need a new rule, and that is rule number 13. And 13 says, if I have a signal that looks as follows, it's 1 over s times tau s plus 1. It corresponds to, in the time domain, to 1 minus e to the minus t divided by tau. Okay, so I'm using this for the inverse Laplace transform for the first term. So this becomes, so I should write this in black, C1 P of t is equal to the first term, which is 5 times 1 minus e to the minus t half And now I do the inverse Laplace transform of the second term, and here I need both number 13, but also number 26. Number 26, I'm just going to write it out because I didn't do that earlier. Number 26 said that if I have a function that is delayed with t0, it corresponds in the frequency domain to e to the minus t0s times the Laplace transform of that function. We actually have to multiply this here with the step function. So it's f of t minus t0 times s of t minus t0 corresponds to this. Okay, so let's go back here. Oh, still in red. So now I need 5 times 1. And now I have to be careful. It's 1 minus e to the minus t minus 0.25, so the delayed version of e to the minus t divided by 2. And then I multiply this with the delayed step s times t minus t0. Okay, so that is my step function. So it doesn't look terribly impressive, but at this point we can try and solve it. Sorry, not solve it. We've solved it. Don't have to solve more. We just have to draw it very nicely. Okay, so let me try and do that. So this is the function up here. What does it look like? So let me be quite careful with the scaling. So this is 1, 2, 3, 4. That should be enough. And 1, 2, 3, 4, 5, 6, 7, 8. So what I would like to draw is first the blue curve, then the red curve, and then I'm going to figure out what the combined curve is, because it's the difference between the two. So let me try and draw the blue curve first, or the blue function. So this is a decreasing exponential that is mirrored along the x-axis and shifted by 1 to further up. So what does it look like? If this is the final value, this is 5. So we end up with 5. But we get there slowly, and we can see the time constant 2. This is our tau for the blue curve. And we can draw a line here from the intersection point between the final value and the time constant. And the curve will approximate or will be asymptotic at the beginning and go like this. So this is why I like to draw this little triangle here with the dotted lines, because this way I get the asymptote at t equals to 0. Okay, so this is the blue curve, and from that I have to subtract the red curve. Now, what is the red curve? Well, the red curve is simply the very same function, only shifted 0.25 minutes to the right. Okay, so I get exactly the same function, only shifted. It only also starts later. So the s of t minus t0 ensures that nothing happens before the time of the delay. Before t0, nothing happens, so everything is 0. And then we go up and we can draw the same triangle with the intersecting line, because the tau, in fact, is identical. It's the same value of tau. So we can draw the same triangle here. It helps us draw the same asymptote. And eventually the two lines will get very close to each other because it ends up being into the very same final value. Okay. So now what is C1 P of t? Well, it's exactly the difference between those two curves. So it will increase and it will decrease. And it gets smaller and smaller and smaller. Okay. So now we may be interested, what is the maximum value? And that is the value as we increase here at time equals to 0.25. So we can figure out what that number is. Or we can also think about it differently, because we can write the red term slightly differently. So let's do that first. So we can write the red term as minus 5 times 1 minus e to the minus t minus 0.25 half times, and so this is true. Or let's leave it like that. Let's simplify it first, or let's write it slightly different, because this is minus 5 times 1 minus e to the minus t half plus 0.25 divided by 2 is plus 0.125. Okay. So now if I have a number a to the b times c, which is b plus c, this is the same as a to b to the b. Sorry, not doing this great here. A to the b times a to the c. So this actually is minus 5 times 1 minus, and now you can see these two terms are additive terms, so I can multiply e to the minus t half with e to the plus 0.125. Now this is only a constant. This is a number, and that number happens to be 1.133 approximately. So something that is slightly larger than 1. And now I can look at C1p of t. Which is the blue term. Let's take the whole 5 out. We just multiply everything by 5 at the end, so I don't have to do it twice. 5 times, and now it's the blue term. 1 minus e to the minus t half minus 1. And now I take this term here plus 1.133 times e to the minus t half. Okay. Oh, this was the red curve actually, so I should have written this in red. Actually, all looks gray on my tablet, so this is minus 1 minus 1.133 times e to the minus t half. And let me do that now in black, because now I can see that this cancels out the 2 1s, and what remains is 5 times. And now I can cancel this out, and this should become a plus 1.133 minus 1 times e to the minus t half. So that leaves me with 5 times 0.133 e to the minus t half, and that is equals to 0.6657 e to the minus t half. Okay, so this means that for t is smaller, or t is between 0 and 0.25, we only have the blue term, which was five times 1 minus e to the minus t divided by 2. Okay, and then if t is greater than 0.25, C1p of t is equals to 0.6657 e to the minus t half. And so what does this mean? It means we have, well, we go up 1, 2, 3, 4, 1. We go up for the first bit very quickly because our final value is 5, but we only reach a value that is much smaller and roughly 0.5. And after that, we go down with the function 0.66 times 5, 7 e to the minus t half. So we go down with the time function, with the time constant 2. I go down like this. So we go up very quickly and we come back down. So if we compare this to our results that we had before, so this we can calculate. This should be the blue term evaluated at time t equals to 0.25. So this is 5 times C1p of 0.25 as equals to 5 times 1 minus e to the minus 0.125. And that is approximately, I think it's 0.882. So that leaves us with very little. So we end up with a value that is roughly 0.5, I think 58 if I remember correctly. Okay. And this is C1p of t. And if we compare this, and let's do gray, with C1 delta of t, which was simpler, much simpler. There's our C1 delta. It's at this point, it's this function here, 0.625 e, and then the time constant. So it's slightly higher, 0.625, but then it goes down quicker because it goes down with the same time function, same time constant. But it's very similar. So this is 0.625 e to the minus t half. Okay. So if I quickly switch to, let me see if it's open. Here we go. If I quickly switch to the book, this is exactly what it looks like, only it's more condensed, so it's more squashed. I've got a higher amplitude, but this is exactly what you see here. These two functions that almost look identical because the only difference is the very short time of the pulse. Okay, so this was C1. So going back to our overview, we've solved our C1 delta and our C1p. So this leaves us to do C2. C2 delta and C2p. Let's choose a different color. Where are we here? This is what we're looking at. So I didn't mean to, it's not meant to underline the delta. I'm just looking for this here. Okay, because this equation is described, these two are defined by this differential equation. But for this, I also need the equation for C1 because C2 requires the knowledge of C1. So let me just highlight where we had C1 delta. This was here. What I haven't done is in the C1P, I haven't added the 1. So this is what I forgot here. So this should actually be this function here. 4 times, sorry, I shouldn't highlight this. Let me just check here. So this is C1P for this time and for that time. And I should actually add 1 in both instances. So I should add +1 here, because remember I shifted it, the concentration by +1, so it doesn't go actually up from 0 to 0.58, but from 1 to 1.58. So I should have a +1 both ways. Okay, so let's carry on with what we would like to do next. C2 delta of t. So to do this, we need the differential equation, which was 3 times dc2 over dt plus 2c2 equals to 2c1. And what we do next is we do the Laplace transform using equation number 24. So hopefully this gets easier the more often you do it. Hopefully you see this immediately. This is 3 times s C2 of s, and this is why I said C2 of 0 equals to 0, plus 2 times C2 equals to 2 times C1. So now I can factor out the 3s plus 2 times C2 equals to 2 times C1. And I can calculate C2 as a function of C1, and that is 2 times 3s plus 2 times C1. And I normally would like to write it slightly differently. I would like to write it in a way that this one here becomes 1. So I multiply both the numerator and the denominator with 1/2. So I get 1 divided by 3/2s plus 1 times C1. And that means our time constant for this process equals to 3/2. Okay. So now I can stick in the values for C1. C1 I've calculated, C1 of s. I can simply substitute that because our C1 delta of s was 1.25 divided by 2s plus 1, if you remember. And now I can stick this in here. And I can calculate C2 in the frequency domain as 1.25 divided by 3/2 over s. So 3/2 times s plus 1 times 2s plus 1. And this I can look up in my table, and I need yet another equation. That is equation number 10. And that says if I have something that looks very similar to this, I look at it and I see something called tau 1s plus 1 times tau 2s plus 1. And that corresponds in the time domain to 1 over tau 1 minus tau 2 e to the minus t divided by tau 1 minus e to the minus t divided by tau 2. Okay. So now I can do the inverse Laplace transform using equation number 10 in the lookup table, and I get this should be C2 delta of t equals to Now my tau 1 is the larger one, that's 2. And my tau 2 is the smaller one, that is 3/2. So I get tau 1 minus tau 2 is equals to 1/2. So 1 over 1/2 is 2. So I have 1.25 times 2 is equals to 2.5 times e to the minus t divided by 2 minus e to the minus t divided by 3/2. T divided by 3/2 is the same as 2t divided by 3. And now this is my equation. In the textbook, it's 3,136. This is my equation for the first half. This is what I wanted to calculate. So I should take my highlighter and make this green. Yeah. And I can also go back up in my checklist and see what I wanted to do. Oh, we've done a lot. We've done this one here. So now what remains is the last complicated bit. And that is to take the same model as before. So C2 equals to 1 over 3/2 S plus 1 times C1. But now my C1, I use the P, and that is 5 times 1 over S minus 1 over S e to the minus 0.25 S. Okay, now I have to stick this guy in here. So if I do that, I get C2P of S equals to, and now I do the blue part and I do the red part. So let's do the blue part first. It's 5 times, sorry, this is wrong. This is not, I was too happy. This was too quick because unfortunately this is only the pulse, but we have to multiply it with 1 divided by 2S plus 1. Thank you. So I could also, let's do this first here. Let's stick this in. So we're getting 1 divided by 3/2 S plus 1. Well, let's say it's 5. Let's put the 5 to this point. Times S times 2S plus 1. Now let's do the bracket. 1 minus e to the minus 0.25 S, like that. Okay. So let's do a red part and a blue part again. So the blue part will be the 1, and the red part will be this guy here. Okay, let's start with the blue part. So we have C2P. Let's do the first bit. We'll just not call it anything. Let's just write it down. It's 5 divided by S 3/2 S plus 1 times 2S plus 1. And now I need yet another rule, and that is rule number 20. You have to be very patient for this video. Rule number 20 says, if I have something that looks like that, 1 divided by S tau 1S plus 1 times tau 2S plus 1, it corresponds in the time domain to 1 minus 1 over tau 1 minus tau 2 e to the minus t divided by tau 1 minus e to the minus t divided by tau 2. Whew. Okay, so now I can take the blue part and I can do the inverse Laplace transform with this. And I get C2p of t, so this is maybe the first one, the blue part. So this becomes 5 times 1 minus tau 1 minus tau 2 was 1/2, so it's 2 times e to the minus t half minus e to the minus 2t divided by 3. Close this bracket. And the red term is exactly the same, only that I now have to move the function, the exact same function, only moved. So this is now C2P2 of t equals to 5 times 1 minus 2 e to the minus t minus 0.25 divided by 2 minus e to the minus t minus 0.25 divided by 2. And then I have to multiply it with a shifted time constant. And you may complain and say, well, there's no s of t step in here, in this function, the blue function. Well, you're right to complain, because actually it should say here s of t, because it's only valid if t is positive. Okay, so that's quite something. Sure. Okay, so this means this function is true, or this C2p of t equals to the blue function C2p1 of t, and that is for 0 is smaller than t is smaller than 0.25. And again, I can add the two. I have to add, so I'm not going to do that now. But this is the function effectively C2p1 of t plus C2p2 of t for t is greater than 0.25. And that simplifies slightly because I have the 5 here and I added the 5 here. So this should be a minus here. Forgot the minus from up here. Okay, so this minus, now this looks like an equal sign. Let's take this out. Minus e, like that. Okay, so this should obviously be a minus. So if I subtract the 2, the 1 here cancels out. And then again, I can simplify it because I can multiply the plus 0.25 half out, and then I have a factor of e to the minus t half, and again here I have a factor of e to the minus 2t divided by 3, not 2. Yeah. Okay, so what does it look like? So let's go back to let's draw a line under here. This was a huge effort. The thing why I've decided to show you all of this is because in the textbook you find the same, but I think it's left out. Many of these little steps have been left out, and I also wanted to show you why these particular Laplace transform in these particular numbers. For example, here, let's highlight them in pink. So we had number 20, and what else do we have? We had number 10, we had number 24. We have, do you see another one? 26, number 13. These are the most commonly used Laplace transforms. 26 again, number 2, number 6. So effectively everything that's important was done and used in this example, number 1 as well. Yeah, so we used loads of Laplace transforms that are very useful. We've done all of those. We've done the different C2s and C1s, and yeah, we can finally say what the answer is. So I don't want to draw the answer here. I would like to go and show you the answer here. So this was the answer for C1. This is what the concentration looked like. And you can see this is a very good approximation using the impulse and not the pulse. And then here is the concentration for C2. Please note it's been shifted by 1, so our results don't exactly look the same. They start at 0 and they go up to 0.27 or something thereabouts. Yeah. Okay, so they're almost the same. Yes, so this is what was done here in 2 pages, which I felt was a bit short. Actually, it's not quite short, but I thought this is very complicated. So I thought, let me give you a video on this and show you exactly which Laplace transforms you need, how you need it, how you use it. And in the next section, we'll see why it's so important to use Laplace, because you can simplify processes so easy. We already saw that we had something very useful, and that was that we have the system separated, these 2 tanks separated in 2 transfer functions. And that is very useful. So what we're going to learn as transfer function, that's also very useful. Okay, so I hope you tried it yourself first, and I hope you learned this wasn't too tedious, and I hope you brushed up your math skill a little bit with this as well. And yeah, good luck doing your own examples.